Hi, there's been a lot of talk in the news and online recently on whether certain medications cause autism. So I thought this would be a perfect time to review a key topic in machine learning and statistics, spurious correlations. Understanding spurious correlations and hypothesis-based science provides the foundations for interpreting research studies. Importantly, spurious correlations is a core concept in machine learning. Understanding them will help you become a true machine learning expert. Before we get started, I want to make it extra clear that this is not medical advice. This video is solely about spurious correlations, the scientific method, and machine learning. It is not medical advice. So, let's get started. To better understand or better explain what spurious correlations are, let us consider the following example. In the US, crime is highly correlated with the consumption of ice cream. You heard me right. The more ice cream people consume, the more crime people commit. What's going on here? Is the consumption of ice cream truly leading to more crime? Of course not, right? It would be absurd for us to even suggest that. Obviously, something else is at play. Well, what happens is that when the weather is good, when temperatures go up, then people consume more ice cream, don't they? At the same time, when the weather is good, people commit more crime. Why? Because it's more difficult to commit crime when it's pouring rain out there or when we're in single digits or below zero. So, of course, both variables, ice cream consumption and crime, are highly correlated. But there is no direct interaction between the two. There's only an illusory interaction through some other variable, right? A hidden variable, if you will, that affects the two original ones. Okay, so why do we get confused by this all the time? Why do we usually find bogus and false correlations? The reason for this is that this is how we have been educated. We have been taught that if two events happen simultaneously or one after the other in sequence, that somehow there might be some relationship between the two. This actually goes all the way back to the Chinese and Greek philosophers. For example, in Greek philosophy, Greek philosophers believed that valor came from the gut and that love came from the heart. And why would they believe that? Well, because when you went into battle, you felt it in the gut, and when you were in love or love ended, you felt it in the heart. For crying out loud, to this day, we're still using the sentence, "I am heartbroken," as a reference to this. But we now know that this is completely bogus, baloney. Of course, valor and love are not originating in the gut or the heart. They're originating in the brain. Now, today we know that our brain, is that hidden variable that the Greek philosophers were not aware of, and that obviously our brain interacts with our organs through the central nervous system, and that's why we might feel valor in the gut when we go into battle and love in the heart. But it is originated in the brain and sent through to those organs through the central nervous system. That's how our emotion system works. Unfortunately, understanding and uncovering these hidden variables is really difficult, and it takes years, sometimes centuries, for scientists to uncover them. In short, science is hard and slow. Now, it is imperative that we understand that machine learning is no different. Machine learning is nothing else than a function f of x equals y. Here, x is the input variable and y the output variable. And then f, it's a mathematical model. That's why AI models and machine learning models are called models, because f is a mathematical model. Now, when we're trying to map a variable x to a variable y, say X is images of faces, human faces, and Y could be a symbolic label like the gender or the perceived gender of the human face, say male and female. Here, what the machine learning model is trying to do is to find correlations between the pixels in the input image X and the symbolic variable, output variable Y. The problem with this is that machine learning algorithms like a neural network find these correlations or extract these correlations from training data. And the majority of faces that we have available to us to train our models, at least the majority of images that are freely available somewhere online that we can easily use, they come from Western cultures. And as you know, in Western cultures, most males have a short hairline and most females have a longer hairline. In some cases, males even have facial hair. So obviously, a neural network learns to associate hair features with gender. The problem is that if I now put my system in production and a male with a longer hairline or a female with a short hairline come into my system, the system might respond incorrectly, might provide a wrong response. In fact, it has been shown that this gets worse the larger, the bigger, the deeper the network is. That is, the more capacity, the more parameters that my network has, the more it falls into this spurious correlation trap. There are solutions to it. One obvious solution is to use a more balanced data set, but good luck with that. Those are usually not available. So a second solution is to weight different samples differently. So for instance, I could tell my loss function to pay more attention to samples of men with long hairlines and females with shorter hairlines than the counterparts so that I balance my training. But a third and preferred approach is to use an ontology, to add an ontology into our machine learning system. I have plenty of courses I have taught over the years and are available on my website. So you may want to go there if you're interested in this topic. But in short, an ontology is information that the machine learning needs in order to come up with correlations that make sense. In our original example of ice cream consumption and crime, it needs to understand that weather is the variable that affects these two events. Then, and only then, we can guarantee that the network will avoid this type of spurious learnings. And that's how an ontology can be used to avoid at least the great majority of spurious correlations. Now, to correctly interpret scientific studies, we must also understand how they are conducted. First, we have the observation. That is, we can use a statistical analysis, like a machine learning algorithm, to come up with a hypothesis. For example, in our previous neural network example, we identify facial features that correlate with gender. Seemingly, in a medical setting, we may look into which people develop a certain medical condition after being or not being exposed to a certain compound. Note, these are a posteriori observations, after the fact, meaning the event has already happened, and all I can do is to do some statistical analysis on it. But if I want to come up with a strong theory, a strong scientific theory, I need to use these observations to define a hypothesis and then test it on new data. For instance, if my neural network tells me that hair features determine gender, I can take this as my hypothesis and then test it on some experiments. In one such possible experiment, I can generate images of human faces where I show the human faces, the photos, without any hairline. And I can show these images to human participants and ask them, please tell me what's the gender of the person in the photo. If my human participants are unable to detect the gender in those photos, then yeah, my hypothesis has some support, right? maybe I am right. But if my participants, my human participants, can still tell from these photos without any hair, they can still tell the gender of those people, then my hypothesis is false. It's been invalidated. It is key to note that this is now a priori statement. I am making a claim before running any experiments, before acquiring any new data. That is, I make a hypothesis. Hair is essential to determining gender in face images, for example, and then I test it in an experiment. I must make my assertion before running the experiment. Contrast this with my observational study that I had before, which was a posteriori analysis. In other words, we want our model to predict what has not been seen or what has not happened yet, rather than describing what's already been observed. This scientific approach, called hypothesis-based, is the gold standard in science. With a hypothesis in hand, I can design numerous experiments to test it. If the results of my experiment, all of my experiments, are in favor of my hypothesis, it does not yet prove that my hypothesis is true. It just means that I have support for my hypothesis. Why? Well, because I can always later on come up with a different experiment where that proved my hypothesis wrong, right? And of course, if I just have that one, a single experiment that shows that my hypothesis is wrong, then my hypothesis is wrong. It's been nullified. Now, if I run more and more experiments and more complex experiments, then it is true that I gain certainty on the truthfulness of my hypothesis. A clear example of this is Einstein's theory of general relativity. It has been tested to death, and every single time, every single experiment has been in support of Einstein's theory. Thus, today we have a strong certainty on that model. Okay, let's now turn our attention to autism. What do we know? To be precise, scientifically precise that is, we will talk about autism spectrum disorder, or ASD for short. What does this mean? Spectrum means that it's not just a single condition, but rather a number of them. To make things more complicated, the definition of this spectrum has been changing over the years. Years ago, when we were using DSM-3 to make the diagnosis, DSM being the manual used to diagnose ASD and other pathologies, the spectrum was quite narrowly defined, hence it included a smaller number of cases. By DSM-5, which is a manual that is being used today, much larger number of conditions is considered. This makes it difficult to transfer any learnings that we might have obtained with previous data to the new cohorts, because some of the groups had not been included in the past. The other problem that we have with ASD, as its name implies, is that it's a disorder, meaning it's not a disease. A disease is a physiological or biological illness that typically has some identifiable underlying cause, right? Many times characterized by abnormal structure or function. Let's clarify with an example: cancerous cells. An oncologist would usually extract some tissue, right? Some tissue from a patient, and then put that tissue under a microscope, look under the microscope, and the oncologist can see whether this is a cancer cell or not, right? This is a medical test. In contrast, a disorder is a collection of signs or symptoms, usually with known or hypothesized associations or associated features that are presumed to be related. Its diagnosis is much more difficult because it typically includes measures that are subjective. Interpretation of such measurements may also vary from locale to locale, from place to place, and may change over time. This, again, makes the observations taken in a specific place at a specific time difficult to interpolate to other places and times. In addition, in recent years, a screening of ASD has increased. While this is a good thing, it yet again complicates the transfer of learning of older cohorts to newer ones. What we do know is that about 80% of ASD is heritable. Hence, there is a potential 20% that may be caused by the environment. This is the percentage we're interested to study here, but with the caveats that I already stated. So, what studies have been completed? Many of the studies are a posteriori analyses. That is, we check on the use of a medication, a compound like acetaminophen, after we detect ASD, and we compare those results with a group where there is no ASD diagnosis. Some of these observational studies have shown an association between frequent and long-term use of acetaminophen during pregnancy and a small increase in neurodevelopment consequences like ASD. Some other observational studies, however, have shown no effect, and yet others have shown a negative correlation. That is, taking acetaminophen may have a protective effect. So, what gives? Well, it is possible that there are hidden variables we are unaware of. But how could we test for those? The problem is that we are unable to conduct hypothesis-based studies. Why? Because we cannot risk the well-being of mothers and children. Imagine the following completely hypothetical, fictitious case. Let's assume that based on some observational data, some scientists out there hypothesize that a specific genetic variation causes some underlying condition, and that underlying condition in mothers actually make them consume more acetaminophen. The scientists may further hypothesize that this same genetic variation has a small increase to their offsprings to develop neurodevelopment outcomes like ASD. This doesn't mean that any previous observations that we had were nothing else than spurious correlations. Again, I want to make this clear. This is a hypothetical, fictitious example, not an actual hypothesis. In this hypothetical situation, scientists may want to define experiments where the mother is given multiple mothers rather, are given different doses of acetaminophen, allowing them to confirm whether indeed the dosage is relevant for the outcome. But this would be an unethical study. By doing so, these scientists may put the life of the mother and the child at risk. This is unacceptable, cannot be done. In short, we're kind of stuck here. We're kind of stuck to a posteriori observational studies. As an alternative, we can run hypothesis-based studies in mouse models. But, mice are not human, and transferring the data from mice to humans, it's again difficult. Remember, we could also improve our observational studies with the use of a well-defined ontology. Unfortunately, again, such an ontology is not yet available. We have some draft ontologies, but due to the heterogeneity and the reification of neurodevelopment disorders, these are generally not helpful. Nonetheless, acetaminophen is generally considered much safer than NSAIDs, and not taking any medication may lead to even worse outcomes, since fever and other underlying conditions are quite dangerous to the mother and the fetus. That's why it's important for mothers or expecting mothers to really consult with their doctors. So there you have it. Thus far, we only have limited observational data. The data may suggest hidden variables are at play, but which ones, if any, is unknown. And we do not have a good ontology yet that can aid in those observational studies, nor can we easily perform hypothesis-based testing. With that, I hope this lecture has been useful and has clarified the role of spurious correlation in machine learning and other sciences. As a reminder, nothing I said here is medical advice, nor should it be taken as such. This was a presentation on the spurious correlations and how they affect observational studies. If you find this helpful, I have a number of courses and lectures available on my website, alish.ai. So if you're interested, I'll see you there. Thank you.